Hi, so for today we're going to talk about electromagnetics. This is my very first video in electromagnetics as requested by our viewers. So this will be the very first video that I'm going to make all about electromagnetics. And in electromagnetics, it is important that we understand the concept of vectors. So for our first lesson, we'll be dealing with some vector analysis as this will be useful for our study of electromagnetics. So let's start. So, scalar and vector. So, scalar and vector are two quantities that are most common. Probably we encounter it already on our physics subject. But it is very important that we have to recall these concepts. Okay, what is scalar? A scalar is a quantity whose value may be represented by any single real number. Okay, so scalar quantities are also quantities that has only magnitude. Okay, never a direction because a quantity that has a magnitude and direction is what we call the vector. But without the direction, only the magnitude, that is what we call the scalar. So some of the examples of scalars are length. Okay, it does not have any direction. Temperature, well, of course. Voltages. These are examples of scalar quantities. But for vector, so for vector, we have the force, acceleration due to gravity. Okay, so always going down. Electric field, for a positive charge, it always emanates outward, and for a negative charge, emanates inward. So acceleration due to gravity, those are examples of vector quantities which has both the magnitude and direction. Okay, so we have also what we call the scalar fields. Okay, and the vector fields, well, of course, example of scalar field is a temperature throughout the bowl of soup. Okay, bowl of soup. So all throughout the bowl of soup, the temperature is actually constant. That is a scalar field. Okay, we can actually get the direction of the temperature because it's a scalar quantity. But for example, for the magnetic field of the Earth, at any point, let's say if we're going to put it into a coordinate system, there is the magnetic field of the Earth. It varies from any point of the coordinate as well as, of course, its magnitude and direction. Okay, so magnetic field, so that is an example of a vector field. So, vectors in our study will be always in boldface, though sometimes vectors are actually represented by an arrowhead. Okay, a letter, a quantity, or a variable with an arrowhead. Okay, while scalars in italics. Okay, so vector algebra. So we can always add, subtract, multiply a scalar multiple to a vector. Okay? So two vectors may be added graphically either by drawing both the vectors from a common origin, which is this, the common origin, and completing a parallelogram or by tip-to-tail method. So we can add vectors by parallelogram method. This is the vector A, vector B. As you can see here, the resultant, or A plus B, is drawn from the origin, common origin of both vectors A and B, and drawn towards here because this line, dash line, is a projection of B, and this dash line is again a projection of A, so that it's A plus B is the vector here. So hence you are forming a parallelogram. And another one is the tip-to-tail method. We can always freely move the vectors anywhere in point in space, given that we are not actually trying to change its magnitude and direction. As long as we are not changing the magnitude and direction of a vector, we can always freely move them in a coordinate system. So, in this example, vector A is chosen as the first vector. So, by tip-to-tail method, we're going to attach the tail of vector V on the tip of vector A. Okay, so such that it happens, this image is the result of that. So the tip of vector, the tail of vector B connected to the tip of vector A, and then from the very first tail of the first vector, which is the vector A, down to the very last arrowhead, okay, or tip of the very last vector, that is the vector A plus B. That is what we call the tip to tail method. And we can also choose vector B as our first vector and then move this vector A such that its tail is connected to the tip of vector B, and hence we are still having the same vector A plus B. So in any way, we can always add them from tip to tail or by parallelogram method. So the rule for subtracting vectors, okay, is to negate one of the vector then perform the addition. So negating the vector only means that we are always changing its direction. Okay, so such that we have an equal vector p here. If we negate one vector here, such that it become negative p, it only changes its direction. Okay, so it would not affect its magnitude, meaning the length of the very vector, because we only multiply negative to our vector. Okay, so that's the meaning of negating the vector. It simply changes its direction. So, vector can be multiplied by a scalar. Okay, but the only thing that changes is the magnitude, except for -1. Of course, if we multiply a scalar multiple of any number to a vector, it always changes the magnitude, meaning the length of the vector. Okay, so, and if we multiply again -1, well, of course, it changes its direction. And as well as if we multiply any negative number, it changes its direction and, of course, its magnitude. Okay? So, multiplication of a vector by a scalar obey the associative and distributive laws of algebra. So, for example, we have scalar E here, R plus S, and we have vectors here in boldface, A plus B. So, we can actually distribute this R and S respectively for our vectors because it obeys the associative and distributive laws of algebra, such that we have this equation now. And if we're going to multiply this, we will be having R multiplied by vector A plus R multiplied by vector B plus A plus S multiplied by vector A plus S multiplied by vector B. Note that these R and S are scalar, meaning they are actually real numbers. It can be a negative or a positive numbers. The only thing that affects the vector when we multiply it by a scalar quantity, okay, again, it only affects the magnitude, except for a negative value of scalar, okay, which affects its direction. Okay, so in rectangular coordinate system, in dealing with electromagnetics, we have the three rectangular system. So what will happen here is that we have x, y, and z, okay, plane. And the relationship with this x, y, and z plane is that they are mutually at right angles to each other. So meaning, if we get the angle from x to y, that is 90 degrees. Okay, if we get the angle from y to z, that's also 90 degrees. Z to x, that is also 90 degrees. So that they are mutually right angles at each other. So we chose here the origin as the intersection of all the points of x, y, and z. So this would be the z plane is equals to 0. If we have a point lying solely in this, so if in this, lying solely on this, we have an x is equals to 0 plane. Okay, so purely on the y and z. And if we have a point here, y is equals to 0 plane. Ibig sabihin, okay, the point always lie on the z and x axis only. Okay, so plotting coordinates. So it is very simple to plot coordinates for x, y, and z. It is also always also has a similarity when we are plotting points in x, y. So for example, let's try to plot these points 1, 2, 3. So, meaning 1, okay, 1 unit, okay, positive unit from the origin to the x, this is that, okay, this is 1, okay, then 2 units from the y. So, basically, here we have 1, 2, this is the 1, 2, 0, but it has a 3 value of z, so you're going to step up 3 times because this is 1, 2, and 3. So hence, this is the point 1, 2, 3. So that is how we plot x, y, z coordinates. Okay, so given that you have a good, well, of course, sketch and dimension or consistency in graphing these points. So, of course, the same for q. 2, negative 2, 1. So we have x of 2, which is this. Negative 2 of y. So 1, 2. To the left of the y plane is the negative. Then, of course, one step ahead of z. Okay? So here is the point. Negative or 2, negative 2, and 1. And of course, we have also the differential volume. If we take, for example, a differential values of dx, dy, and dz, we will be arriving at the differential volume of this, wherein our volume is simply, we will get dx, dy, dz. We multiply that. So it actually corresponds to a, let's say, a cube, okay, because the volume is dx, dy, dz. So if we make a cube using dx, dy, and dz, as we can see, we have a point here. So this point will become dy, dz. Why? Because it only shows the y and z. Okay? If that point is in the side of the space of the cube, dx, dy here, because why? No z, because there is no height in here. And we have here dx, dz. Why? Because there is no y direction in this face of the cube. And of course, the horizontal is dy. This line is dx because it corresponds to this. And dz is the height, which corresponds to z axis. Okay? So, vector components and unit vectors. So to describe a vector in the rectangular coordinate system, let us first consider a vector r. So vector r extending toward from the origin. So this vector r extending from the origin toward any point in the xyz plane can be rewritten as vector r is equals to x plus y plus z. So vector r drawn. Why? Because if we get, again, by vector analysis or by vector addition of vectors, okay, we have x here. If we move this vector x here, because we have x here, we move this vector x here such that we place the tail of this vector x to the tip of vector y. Here is our vector. But take note, you also have z here, so that if I'm going to move this z here and place its tail to the tip of vector x here, connected here, I will be having this vector, okay? Such that I form a triangle. And by the vector, okay, by the vector addition using tip to tail method, we're going to draw the vector r from the very tail of the first vector, which is y, up to the tip of the very last vector, which is z. So as you can see, that is the vector drawn xy, x plus y plus z. Okay? So we have also unit vectors. Unit vectors are actually the vectors that has a magnitude of 1. Okay? Hence the term unit. So in this study, we're going to have unit vectors in xyz as ax, ay, a sub z, to denote that that is a unit vector. Okay. Finding the vector from 2 points. So, to find the vector formed by 2 points, we simply subtract their coordinates plus their unit vectors. So, for example, we want to find, we are given 2 points in the xyz plane coordinate. So, we have 1, 2, 3, 2, negative 2, 1. So, if we're going to get the vector from point P to point Q, hence, denoted by R sub PQ. So it means from point P to point Q, what are we going to do is to simply, what? Subtract their unit vectors. Unit vectors is from the origin, R sub Q and R sub P. Well, of course, how do we get that R sub 1 and R sub Q and R sub P? Well, of course, from the origin. So 1 minus 0, 2 minus 0, 3 minus 0. Okay, hence, that is the R sub Q. R sub Q, okay, and R sub P is this. So what are we going to do is simply to get the vector emanating from R or from P to Q, we simply what? Subtract its coordinate. And we're going to put vector, unit vectors AX, AY, and AZ. So in this case, if we want to get the vector from P to Q, we're going to subtract 2 from P to Q. So it means the terminal point is the Q. So that is the first one we're going to subtract. So we have 2 minus 1 We have negative 2 minus 2. Okay, that is plus. Okay, then 1 minus 3. Okay, I forgot to write the 1 minus 3 here. So what will happen here is 1 minus 3 az. So we have a sub x, negative 2 minus 2 is negative 4ay. Okay, then 1 minus 3 is negative 2az. Hence, the vector from R, or from P, from point P to Q is given by this vector. Okay, okay? So that's how we find the vectors. So we have what we call the magnitude of the vectors and uh, the unit vectors. Okay, so any vector B then may be described by its magnitude given by this equation. So magnitude is represented by like an absolute value. Okay, but me, when I'm teaching vector analysis, I always use the double absolute value, let's say, to denote that it is different from the absolute value. Well, by the book, it says that if we have an absolute value, let's say a parallel line in between or inside, and inside of that is a vector, so that is denotes the magnitude of vectors. So what is the magnitude of vector? Again, if we're going to go back, the magnitude of the vector is the length of the vector. So we can get the magnitude of the vector by this formula. We have the square root of the x squared component, scalar component of the x, plus the scalar component of y squared, plus scalar component of z squared, and then here we have the square root. Note that if we get the magnitude of any vector, okay, if you're going to get the magnitude of any vector, the result is always a scalar quantity. Okay, so we have now what we call the unit vector again. How do we find a unit vector? Okay, from a vector. Okay, so any vector can become a unit vector by dividing it by the vector's magnitude. So therefore, we can get a unit vector of any vector. Okay, if we want to get a unit vector of any vector, we can use this formula. Okay, we can use this formula. Meaning is that no, it's actually this is not magnitude of b. Okay, this should be written as, okay, this should be written as a b. Okay, that denotes the unit vector. Okay, pardon me. Okay, this should be rewritten as a sub b to denote a, that is a unit vector. Okay, so in order for us to get the unit vector of any vector, a sub b denotes the unit vector, we need to have the vector divided by its magnitude vector. Okay, so as you can see here, b over the magnitude of b, okay, which is this magnitude is equal to this, okay, as we have shown it a while ago. And again, if we get the unit vector of any vector, the result is always a vector. Okay, remember that. Okay, so let's try to have a sample problem. So let's try to solve some problems. Specify the unit vector extending from origin toward the point G to negative 2, negative 1. Find also its magnitude and the desired unit vector. So it says from the origin, which is the coordinates of the origin 0, 0, 0, to point G, which is actually 2, negative 2, and negative 1. So this is our terminal point. This is our initial point. Therefore, the vector G, okay, I'll try to write this in bold face. Okay, vector G is actually what? Terminal point is this 2 minus 0. Terminal minus initial multiplied by the unit vector AX, plus we have terminal for Y, negative 2 minus 0. We have AY, unit vector, plus lastly we have negative 1 minus 0 AZ. Simplifying, we have 2AX minus 2AY minus simply AZ. And this is the unit or the vector, unit vector from origin toward that point G. Okay? So find also the magnitude and the desired unit vector. So to get the magnitude of the unit vector, we simply denote it as like the absolute value. And we have the formula a while ago. Okay? The components. Okay? We're going to add the square of the components and take the square root of them. So we have here 2 squared because of this plus negative 2 squared. Okay? No problem. Even if it's negative because it's raised to squared. So any number raised to square, even if it's a negative, will still yield to a positive value. So plus negative 1 squared because the component of this is negative 1. That is square root of 2 plus 4 plus 4, 8 plus 1. That's square root of 9. And that's equivalent to 3. That is the magnitude of the vector g. As you can see, this is a scalar quantity. Okay, this is a scalar quantity because if we take always the magnitude of any vector, it's always a scalar quantity. How about the desired unit vector? The desired unit vector, okay, of a g, okay, is actually equal to what? The vector g itself, okay, the vector g itself over what? The absolute or the magnitude of the vector g. Okay? So the vector g is what? This vector. We have 2ax minus 2ay minus az over the magnitude of the vector g is 3. Okay? Hence, our answer should be, okay, 2/3 ax minus 2/3 a sub y minus 1 over 3 a sub z. Or in decimal, that is equivalent to 0.0667 ax minus 0.667 ay, if I'm not mistaken. Okay? Okay, minus 0.333 az. Okay? That is our answer. Okay. So this is the vector or the unit vector of that vector g. Okay. Okay. So let's try again. Number 2. We have 3 points. Given points m, negative 1, 2, 1, and 3, negative 3, 0, and p, negative 2, negative 3, negative 4. Find the following. Okay. So, R sub mn. So, what does this mean? Okay, the unit or the vector from m to n. Okay, from n to n. So, as we can see here, from n to n, so our terminal is n. So, what are we going to do is to simply subtract its coordinates and write a what? A unit vector ax, ay, and az. So, what will happen from n to n? This is our terminal point, so that means 3 minus the x component minus negative 1 ax by 3 minus negative 1, be careful for that, plus, of course, we have what? Negative 3 minus 2 ay, okay, plus we have 0 minus 1 az. So our answer should be negative times negative is plus 1. So we will be having 4ax here. Negative 3 minus 2 is negative 5ay here. 0 minus 1 is negative az here. So that is the vector from m to n. Okay? Resulting unit vector. Okay? Okay? Vector from n to n. So let's try to solve the letter B. We have vector from R mn plus R from MP, R sub MP, which means vector from M to P. So we already got the vector RMN. How about the vector RMP? Okay. So our final point here is the P. Initial is M. So we have negative 2 minus negative 1 AX plus we have negative 3 minus 2 AY plus negative 4 minus 1 negative 4 minus 1 A sub Z. So evaluating negative 2 plus 1 is negative ax. Okay? Negative 3 minus 2 is negative 5a sub y. Negative 4 minus 1 is negative 5a sub c. So, we can now perform vector RMN plus RMP by simply adding, okay, by simply adding the components. Okay? So, we have 4ax plus negative ax is simply what? So, that is 3ax. Okay? That is 3ax. So, I will show you how. Again. So, the components, 4 and y, 1. So, we have 4 minus 1 ax plus we have negative 5 minus 5 a sub y plus we have negative 1 minus 5 a sub c. Hence, our answer would be 3ax, okay, minus 10ay minus 6a sub z. So this should be our answer for our problem letter B. So let me just rewrite this. A sub x. Okay? So a sub x. That must be our answer. For letter C, it says the magnitude of the unit vector Rn. So if we see this sign, okay, it denotes that the magnitude of Rm. So our result here should be scalar. But first, we need to find the vector Rm. What is a vector Rm? It only says that your initial point here is the origin. Okay? So if the initial point is the origin, your final point is M. So let's label this our M. Let's copy this. Let's just copy negative 1. We have 2 and 1. So if your initial point is the origin, the final point is M, you're going to what? To get the vector, multiply or minus again, negative 1 minus 0. This is the final point, initial point, AX, plus, okay, final point of 2 minus 0, a sub y, plus final point of 1 minus 0, a sub z. So we have now negative ax plus 2a sub y, okay, plus a sub z. Okay? Okay, so the magnitude, we are asked for the magnitude. So we can get the magnitude. We have now the vector here. So what is the magnitude? Negative 1 squared, because the value of here, the coefficient here is negative 1, plus 2 squared plus 1 squared. And that is equivalent to, if you calculate it, 2.45. Hence, the magnitude of this vector is 2.45. Okay, and for letter D, okay, for letter D, a vector, unit vector of a MP. Okay, do we already have MP here? Yes, we have already the MP here, and our MP, vector MP, is actually this one, negative ax. So we have negative a sub x minus 5ay minus 5az over, this is a unit vector. Okay? Desired unit vector. So this is the vector MP. And remember, we're going to get the unit vector by what? We have the numerator, the vector itself, divided by the magnitude of the vector itself. So what are we going to do? Okay, divide it by the magnitude of this. So we have negative 1 squared plus negative 5 squared plus negative 5 squared. Okay? So if you divide that, what will happen? By your calculator, okay, 5az, this should be square root of 51. Okay? So if you calculate that, we have negative 1 over square root of 51 ax minus 5 over square root of 51 a sub y minus 5 over square root of 51 a sub z. So if you simplify this, your calculator would give you what? Negative 0.14 a sub x, negative 0.7 a sub y minus negative 0.7 a sub z. And this is the desired unit vector of MP. Okay, the vector MP. I hope you can follow what I'm trying to say here. Okay, so moving on for our problem, let's say number 3. Okay, number 3, given vectors m negative 10ax plus 4ay minus 8az and n is equals to 8ax plus 7ay minus 2az. Find letter A, the unit vector in the direction of negative m plus 2n. Unit vector, that is A, okay, in the direction of negative m plus 2n. So first, before we can get the unit vector, of course, we need to get negative m plus 2n first. Okay? So, let's try this. I will negate negative m, vector negative m. So, that would be negative of the vector m, which is negative 10ax plus 4a sub y minus 8a sub z. Okay, distributing the negative sign, we have 10a sub x minus 4a sub y plus 8a sub z. So, this is our negative n. How about 2n? Twice the n. Okay? This is a scalar multiplied by a vector. So, scalar multiple of a vector. So, we have twice the vector n, which is our n is 8ax plus 7a sub y minus 2az. So, we have 16a sub x plus 14a sub y minus 4a sub z. Okay? So, that should be our twice of n. Okay? And if we're going to perform the algebra, vector algebra of this, negative m plus 2n. So, negative m plus 2n. So, we will add this, okay, by components. So, we have negative m, 10 plus 16, a sub x plus negative 4, this plus 14, a sub y plus 8, okay, plus negative 4, which becomes negative minus 4 az. Hence, our result shall be 10 plus 16 is 26 a sub x. Negative 4 plus 14 is plus 10 a sub y. Okay, let me just rewrite this so that you would not be confused. Ax, okay. Oops. Let me try again. A sub x, okay? 26 plus 10 plus 4 a sub z. So, this is our negative m plus 2n. Okay? Negative m plus 2n. That is not the final answer because we are asked for the unit vector of negative m plus 2n. And the unit vector of negative m plus 2n is negative m plus 2n over the magnitude of negative m plus 2n. And what is negative m plus 2n? That is 26 a sub x plus 10 a sub y plus 4 a sub z over, okay, over, let me just rewrite, over the square root of the components, which are 26 squared plus 10 squared plus 4 squared. Okay? So, let me have this, the answer here. Okay. So, how? Okay. Let's rewrite 26a sub x plus 10ay plus 4a of z over, we have the square root of 6 square root of 22. So, if you're going to divide this all by components, I'm going to copy this first. Okay. Just give me time. I'm just going to copy this to our here so that we can easily see. Okay. So what happens is that when we have this, okay, by component, divide this, plus 10 over 6 square root of 22 a sub y plus 4 over 6 square root of 22 a sub z. You're going to evaluate it, okay, by your calculator. So the result would be 0.92 a sub x plus 0.36, okay, a sub y plus a 0.14 a sub z, which is the desired unit vector of negative m plus 2n. Okay? So, for letter B, we shall be finding again the what? The magnitude of 5ax plus n minus 3m. 5ax plus m minus 3m. So, the magnitude of the vector 5ax magnitude plus n minus 3m. Okay? So, we don't have 3m. Okay? We don't have the 3m. Okay, what is the 3m? Thrice the vector m. So, what is our vector m? Negative 10, 4, and negative 8. Negative 10, 4, and negative 8. No, negative 10, 4, and negative 8 az. So, what will happen? That should be 3 times negative 10 ax plus 4 a sub y minus 8 a sub z. So, this corresponds to negative 30 a sub x. Then, we have plus 12 ay minus 24 a z. Okay? 24 az. So, this is only 3m. If we apply negative 3m here, such that we negate this should be 30 ax plus or minus 12 a sub y plus 24 a sub z. Okay? Why? Because it has a negative here. So, we're going to add this to all of the functions here because to all of the vectors here because we have distributed the negative sign. So, we have 5ax plus, what is our n? Okay, our n is actually 8ax plus 7ay minus 2az. Okay, let me just check it out. Okay, if we have a correct value of n here, 8, 7, and negative 2. Okay, am I correct? 8, 7, and negative 2. Okay, we're good to go. Plus, of course, the negative 3m. Okay, I add it because I distributed already the negative sign. So, to avoid confusion. So, we have 30ax minus 12ay plus 24az. And this is the vector addition of these three, not the magnitude. Still the vector addition. So if we have 5ax plus 8ax is 13ax, okay, plus 30, that should be 43. Okay, so 5ax, let me just rewrite, minus 3 is 5 plus 8, 13 plus 30, that is 43 a sub x. Ay 7, we have 7. Ay minus 12, that is negative what? 5ay, if I'm not mistaken. Then we have negative 2az plus 24, that should be plus 22az. Okay? That is the 5ax plus n minus 3m vector. Okay, if in order for us to get the magnitude of this, okay, it's very easy. Why? Because we're going to get the sum of the squares of the components and then take the square root. So we have 43 squared plus negative 5 squared plus we have 22 squared. And if you're going to calculate that, that should correspond to 48.6. And that is the magnitude of this vector. 5ax plus n minus 3m. Okay? So that should be the answer. Okay, so if we're going to answer letter, let me just copy again the question. Okay. Copy again the question. Going to copy the question. Okay. And put it again let's say on the other. So this would be our letter C. Okay, letter C. So magnitude of m, times the magnitude of n multiplied by the m plus n vector. Okay, we need to do first the magnitude. That's easy. Magnitude of vector m. We get the magnitude of vector m by negative 10 squared, okay, plus 4 squared, square root, plus negative 8 squared. Okay, so if you get the magnitude of this m right here, okay, I think it's 6 square root of 5 if I'm not mistaken. Okay, if I'm not mistaken. So, and then we get the magnitude of vector n. Okay, we have square root of 8 squared plus 7 squared plus negative 2 squared. And that corresponds to, let me just check it again. Okay, so that corresponds to 3 square root of 13. Okay, 3 square root of 13. We have gotten now the magnitude m and n. Okay, but we need to add m plus n. Okay, if we need to add m plus n, so we have negative 10, okay, plus 8 a sub x plus, okay, we have 4 and then plus 7 a sub y plus negative 8, okay, negative 8 minus plus negative 2. So we have az. So what will happen? We have negative 2ax plus 11a sub y minus 10a sub z. Okay? So, again, it's simple. If we perform this, magnitude m times n, okay, what will happen? Okay, so that should be 18, okay, square root of 65. Okay, if we calculate it, 6 square root of 5 multiplied by 3 square root of 13, let's check. 18 square root of 65. Okay, multiplied by the m plus n, which is negative 2ax plus 11a sub y minus 10a sub z. So if we multiply that, our answer should be negative, okay, 290a sub x plus we have 1596.33 a sub y, okay, 33 minus, of course, 1451.21 a sub c. So this should be our final answer. That is the vector we're looking for. Remember, this is a magnitude times magnitude is scalar times scalar is scalar. But we multiply scalar by a vector, so our result must be a vector also. So hence, this is a vector. So this is our result for letter C. So let's go now to our very last number. Okay, last question. Okay, so we have, of course, here vector A extends from the origin to point 1, 2, 3, and vector B extends from origin to 2, 3, negative 2. Find the unit vector in the direction of A minus B. So A minus B is a vector. So in order for us to get the vector A, okay, we need to get, okay, from 0 to origin. From origin to this point, that's the vector A. So 1 minus 0 plus, or 1 minus 0 A sub x. I'm so sorry. That's a vector. We're talking about vector. Plus 2 minus 0 A sub y. We need to find first the vector A and vector B. Okay? So plus 3 minus 0 A sub z. So simply this is AX plus 2 A sub y plus 3a sub z vector. And from the vector b, the same, okay, from origin to this point. So 2 minus 0 ax plus 3 minus 0 ay plus negative 2 minus 0 a sub z. So the result is 2ax plus 3ay minus 2az. It says the unit vector in the direction of a minus b. So a minus b would be, okay, 1 minus 2ax, okay? 1 minus 2ax plus, okay, plus we have 2 minus 3ay plus we have 3 minus negative 2a sub z, okay? So we simply subtract a and b, okay? So what happened was that we have negative ax minus ay. 3 minus negative 2 is plus 5az right here. Okay? So we now get the a minus b. So we are now ready to get the magnitude of a minus b. Okay, we have the square root of negative 1 squared plus negative 1 squared plus 5 squared. So that corresponds to a magnitude of, diba? Magnitude of 3 square root of 3, if I'm not mistaken. So that if we're going to get the direction, okay, the unit vector in the direction of a minus b, we simply use the formula, okay? The unit vector is denoted by a of a minus b is simply vector a minus b over the magnitude of a minus b. Okay? The vector itself divided by its magnitude, of which we got it already. So a minus b is simply negative ax minus ay plus 5az over a minus b, the magnitude 3 square root of 3. So if we're going to get that, what will happen is a unit vector of a minus b is negative 1 over 3 square root of 3 ax minus 1 over 3 square root of 3 ay. Okay, we simply divide the coefficients of this by this. Plus 3 square root of 3 az. And if we're going to have it calculated by our calculator, that is simply negative 0.19 a sub x minus 0.19 a sub y, that is the same, plus 0.96 a sub c. Now, this is the unit vector in the direction of a minus b. Okay? So, for letter B, for our last example, the unit vector in the direction of the line extending from origin to the midpoints of the line joining the ends of A and B. The unit vector in the direction of the line extending from the origin to the midpoint of these two points. Okay? So joining the lines of the ends of A and B. So what are we going to do is first we're going to find the midpoint of AB. Okay? The midpoint of AB is given by x sub 1 plus x sub 2 over 2. So in this case, we have 1 plus 2 over 2 because x sub 1 is 1, x sub 2 is 2. Okay? And we have 2 plus 3. This is y sub 1, y sub 2 divided by 2. And then we have 3 plus negative 2 or minus 2 over 2. So for z. So the x, y, z midpoints are 3 halves. Okay? We have 2 or 5 halves. I'm not, my mistake, 5 halves, 3 plus 2. That is 5 halves. Okay? Then we have 1 half. So that is the midpoint of A and B. The problem is actually asking us, okay, okay, the unit vector of this vector that we're going to form from origin to this AB, midpoint AB. So to get the vector, okay, emphasize the vector, this is only the points of the midpoints of the 2 points given. So we're going to get now from the origin. So this is the terminal point and the initial point is origin. So that's simply 3 halves minus 0 ax plus 5 halves minus 0 ay plus 1 half minus 0 az So it only means that that is equal to 3 halves a sub x plus 5 halves a sub y plus 1 half a sub z. And if we're going to get the unit vector in the direction of the midpoint of a and b, we have the vector of the midpoint of a and b over the magnitude of the midpoint of vector ab. Okay? So we have 3 halves a sub x plus 5 halves a sub y plus 1 half a sub z. Okay? Divided by the magnitude. Okay? So I'm going to make this decimal. 3 halves is 1.5 squared. 2.5 5 halves is 2.5 squared plus 1 half 0.5 squared. So let's try. I'm going to make this again decimal. So 1.5 ax plus 2.5 a sub y plus 0.5 a sub z divided by, okay, divided by that square root. Let me just first calculate it. Okay, so we have square root of 35 over 2. Square root of 35 over 2. And if again we divide this coefficient with this, okay, each coefficient, we shall be arriving at an answer of the unit vector of the midpoints a and b, vector a and b. A and b, we have 2.96, okay, a sub x, that is 1.5 divided by square root of 35 over 2, ax, that's the result. So plus 2.5 divided by square root of 35 over 2, that is 0.85 a sub y. And lastly, we have plus 0.17 a sub z. So this is the unit vector of the midpoint joining the points A and B, the vector, unit vector joining the points midpoint A and B. Okay, so if you found this video helpful, don't forget to subscribe. Thank you so much for listening. This is a lengthy discussion, but I hope you learned something about the vector analysis today in electromagnetics. So thank you so much for listening. Have a great day. God bless you.